Welcome to Investigation 5.3. In this investigation, we're going to be taking those exponent rules that we used in Investigation 5.2 and extend them a bit further into that of rational exponents. In other words, exponents that have that are essentially fractions in and of themselves. They're not going to be whole numbers or integers. So here's our focus question. How are the rules for integral exponents? So integers, we're talking about 1, 2, 3, or -1, -2, -3. How are the rules for integral exponents related to that of rational exponents? So looking at 1.2 or 1/2 or something like that. How are the rules for exponents useful in writing equivalent expressions with exponents? So we're also going to be looking at finding alternate ways to represent exponents as rational numbers, which honestly rational exponents have lots of different ways of being represented. So let's look at some of our rules that we know so far. So here, the very first one, we have the same base and different exponents, and what we found with this one, this is a power product property. Essentially, if we have the same base but a different exponent, we can essentially add our exponents. We have the power to a power property, which tells us if we have a power or an base with a power, and it's also raised to another power, what we can do is multiply those exponents together, because we know that we're just going to be representing the stuff on the inside of this parentheses over and over the number of times that n tells us to. We find that we can just multiply after that with the exponents. We also have sort of a distributive property going on with our exponents. If this exponent is here, we can also rewrite this as saying the exponent can attach itself to just the x and just the y, but we use this more often in its other format where we took the x to the m and the y to the m, so same power, different bases, and we actually multiplied those bases together and put it just to that one single power. We also have the quotient of powers property, so telling us that we have the same base but different exponents, and essentially if we have that sort of situation, we can subtract the first exponent from the second exponent. We also have our other last couple of power properties, which are the negative exponent property, and if we have a negative exponent, another way we can write it is saying it's a division problem. So we'd say whatever we're dividing it by, if there is an actual number besides 1, perhaps it was a 2 times x to the negative first, we would rewrite the 2 on top, but we're then dividing by x to the first power. Now this one didn't have a 2 in it, so we could also write this one as just saying we have our 1 here, and now we're dividing that 1 by x to the first power. And our very last property is the zero exponent property, and that's any number, a half or a million, doesn't matter, or even -274,003. That raised to the 0 power, no matter what, will get us 1. So, our question now is this: do these rules work for rational exponents? So if I had 1/2 for my exponent, or perhaps 1/32, will they work? Will this situation work for them too? So let's get started with a little bit of a thought process. What if we have this amoeba population? It grows a certain amount. Suppose this amoeba population quadruples every week. That means we could write our equation as y is equal to 4 to the x power. So that's how it's growing. Well, what if I wanted to find out how many amoebas there were in just half a week? So in other words, we're finding it at its sort of halfway point. what is that amoeba population? Does it make sense for me to write, instead of just 1 for my week, could I write a half? So I find what it is about halfway through day 3. Does it make sense for me to write an equation like this? Well, first of all, let's think. If it does make sense to do that, I should be able to find my halfway point in the amoebas on day 3.5. I should be able to figure out how many amoebas there are. And if I look at my graph here, that halfway point would refer to this point in time, essentially, where my weeks is halfway in between the 0 and the 1. So if that was the case, it refers to this point right here, and we can call that point half for the weeks, and we have 2 amoebas. So that's just starting out with the very beginning. So 1 amoeba, half a week later, we have 2 amoebas. The end of the week, we have 4 amoebas. So this point is referred to as a half and 2. So let's think about how 4 relates to 2. There's lots of different ways that 4 relates to 2. But we need to somehow get our x value in here. So 4 with our y equals 4 raised to the x power. If we were to put in a half for x, we have now 4 to the 1/2 power is equal to our y. Well, our y in this case is 2. 2 is equal to 4 to the 1/2 power. Well, in all reality, 4, we can have 2 plus 2 equals 4. 2 times 2 equals 4. And we know the square root of 4 is equal to 2. Well, 4 to the 1/2 power is clearly not describing 2 plus 2. It's also clearly not describing 2 times 2. But perhaps 4 to the 1/2, if I look at this, can also be written as the square root of 4. So using this idea, I want you to think about this. Let's think about the rule for adding exponents. So before, if we had a number with the same base, so let's take the number 4 and the exponent 1/2. We know in order to add exponents, we're essentially multiplying a number or 2 bases that are the same together. So essentially, we'd have 4 to the 1/2 plus 1/2. What does that get me? What is 1/2 plus 1/2? 1/2 plus 1/2? Hopefully, you're saying 1. So we'd get essentially 4 to the 1st power. So we have rational exponents, and we just used the product of powers property, which is kind of cool. Essentially, we just added our exponents just like we would if we had the same bases. We have the same bases, we can add our exponents, and we know that the square root of 4 is equal to 2, and the square root of 4 is equal to 2, and 2 times 2 is equal to 4, which is the exact answer of 4 to the 1st power. So, kind of interesting. Let's now think of other ways that we can describe fractional exponents. As of right now, we essentially are saying that, let's synthesize this. We have the square root of x is equal to saying x to the 1/2 power. Let's see if that applies to other things. If we had the number 8, we know 8 is equal to 2 times 2 times 2. So essentially, the cube root of 8 equals 2. Well, the square root of x is equal to x raised to the 1/2 power. The cube root of 8 we could also rewrite this as saying 8 to the 1/3 power. 1/3 power of 8. Essentially, what number times itself 3 times would get me 8? Well, 2 3 times would get me 8. So one more exponent rule that you are going to add is essentially the concept of square roots. Or not square roots. Let's talk about nth roots. Essentially, this is our rule. We have the nth root of b is equal to b times the 1, or raised to the 1 over n. So if we had the cube root of b, that would be equal to b raised to the 1/3, and so on. Using this idea, we're going to play more with our exponent rules. So let's move up a little ways. What is 16 raised to the 3/2? So, a couple ways that we can think about 3/2. We're going to use the power to a power property for this one. If we think about 3/2, we could rewrite that as 3 times 1/2, or 1/2 times 3. It doesn't matter. Both of those are the same thing, but let's play around with this. So we have 16 raised to the 3/2, and we know 3/2 could be written as 3 times 1/2. And so that's 16 raised to the 3 times 1/2. I'm going to now write this, I'm going to break it down. So the power to a power property tells me that essentially one number raised to, or one power raised to another power, we can just multiply them together. So I'm kind of working backwards. So I'm going to now rewrite this as saying 16 cubed raised to the 1/2, so I'm now color coding my half. 16 cubed raised to the 1/2. Let's do a little bit of math. 16 cubed is equal to 4,096. And now we're going to take that, raise that to 1/2. So essentially, what number times itself gets me 4,096? Or what is the square root of 4,096? Well, 64 is. So apparently 16 raised to the 3/2, so essentially 16 times 16 raised to the 1/2, 16 to the first power times 16 raised to the 1/2. Number that multiplies itself to get me 16 is 4, so 16 times 4 is supposed to get me 64, which is exactly what it does. Let's now think of this using this other method. So if we just use this top one, now we're going to use this bottom one. So now we have 16 raised to the 3/2, and we're going to rewrite this as 16 raised to the 1/2 times 3. So let's rewrite this even more. I'm going to color code things now. We have 16 raised to the 1/2, and we're going to be raising this to the 3rd power. Again, the power to the power property split apart. It's working backwards. So, what is the 16 raised to the 1/2? Or what is the square root of 16? That is what that 1/2 is telling me. So what is the square root of 16? And all of this is cubed. What is the square root of 16? I hope you're shouting out 4. And we're going to take the cube root of that. Now, 4 times 4 times 4 equals, so 4 3 times equals 64. Again, the exact same number that we got before. Kind of cool. I'm going to show you one more way that we can solve this same problem. What is 16 raised to the 3 over 2? What is 16 raised to the 3 halves? Using the product of powers property. So if you remember, the product of powers property is telling me that we have a to the m times a to the n, and we're saying a to the m plus n. So let's think of 3 halves, and let's divide it up, or let's break it up into 2 fractions that we can add together. Well, an easy fraction that we can take out of 3 halves would be simply a half. And what would be left over would be 1. So let's break this down. We got 16 to the 3 halves. We can break that down into 16 times a half plus 1. Breaking it up once more, working backwards. So we're no longer, we were here, or we're here right there, and now we're moving to this point. So we have 16 that we can write as 16 to the half power times 16 to the first power. So just right here we have 16 to the first power, which we can rewrite as just plain 16. And then we also have 16 to the half power, or the square root of 16. Those two things are being multiplied together. The square root of 16 is 4, and that's being multiplied by 16, which ends up getting us our grand finale of 64. Again, the same exact answer as before. Playing around with these exponent properties right here. Playing around with these exponent properties can teach us to manipulate numbers in a really neat way. We can manipulate numbers and manipulate interesting roots, or square roots, or cubed roots, or nth roots, to use them with rational exponents. So using this idea of these integer rules, exponent rules, in reality, they can be used for both integers and rational numbers. So play around with this in this investigation. Work yourself through the rest of the investigation. If you have any questions, please ask. This is not easy material, and I by no means believe that you're going to understand it right away. So please ask questions, work yourself through the investigation, and begin working on the homework. Thank you so much for paying attention, and I will see you later.